Hello and welcome back. Next we'll look at timing for latch-based designs. We'll see the similarities and differences in the enabling equations for timing with latch-based designs. We'll see that though latch-based designs have potential to give a little more flexibility in achieving your clock period requirements, they greatly increase the potential for hold violations and thus are not used much in modern designs. Here is the structure of a latch, a D latch. I remind you that the basic functionality of the D latch is that the output Q follows the input D while the clock is high. This is called the transparency region. The value on D that is there before the clock goes low is then what is stored on Q for the remainder of the clock period. Since the latching event is actually the falling of the clock, the setup and hold times are defined with respect to that falling edge. Thus we have T setup and T hold referred to the falling edge of the clock. T clock to Q refers to how long it takes from the clock going high to Q changing. But because of this transparency aspect, we also have a new parameter here, TD to Q, which is the delay from TD changing during the transparency period to Q changing. And again, I remind you, at the bottom left here, we're looking at a similar scenario than we had in the flip-flop based design. Two registers with logic in between them, clock going between them, where the skew on the clock dash is going to the right hand register. So one possibility is to use latches in much the same way you use flip-flops, and that means under the nominal design, under this mode of design, the setup equation is the same as it is for flip-flops. That is, the clock period must be greater than the T clock to Q, the logic, setup and skew times. However, there's another way of using latches which gives some additional flexibility, and that is to actually permit use of the transparency period of the latch. If you just stick to the equation at the top of the page in designing latch-based systems, you are not using the transparency period of the latch. That is, you're not permitting the D inputs to change during that transparency period. However, if you permit the D inputs to change during the transparency period, this can lead to some increased flexibility and is referred to as cycle stealing. Examples illustrated at the bottom of the page here. Here we have 3 registers. There's 2 pipeline stages, T1 on the first set of logic, T2 on the second set of logic. Notice that T1, the delay T1 is longer than the clock period. That is, the D input of this second latch is now changing during the transparency period and the Q output changing TD to Q later. This is perfectly permissible. And you can see in this example here, if the critical path was in logic block 1 and T2 was a faster piece of logic, then this would actually lead us to enable us to actually make a faster clock than if we just stick to the flip-flop based equations at the top of the page. So in this example again, T1 is longer than in the case of the flip-flop. We're exploiting the transparency of the latch. So we permit cycle stealing. The constraints to prevent setup violations change. What's changed here is we've also included this T clock to high min. That is the minimum possible transparency period of the latch. The right hand side is the same as before. So here T clock plus T clock to high min must be greater than or equal to the sum of the delays plus the skew. This is illustrated in this timing diagram below. Again, the worst case scenario for the random skew is when the clock going to the right hand flip-flop, right hand latch, is advanced with respect to the clock going to the left hand latch. Now, we have from this time here to this time here, that is plus t clock to high min later. For all these events to occur, t clock to q, t logic, plus t setup before the falling edge, plus t skew. In this example here, the setup constraint is satisfied by the amount t slack. There's a couple of notes at the bottom here. The percentage of time that the clock is high, that is t clock high as a percentage of t clock, which is the clock period, is referred to as the duty cycle. And I just point out, in Synopsys Design Compiler at least, the default is that cycle stealing is not enabled. Not that this matters much practically for the purposes of this class, because we're not going to use latches in our design, for reasons we'll see in a moment. So cycle stealing is not a universal solution that allows you to run your designs higher by the duty cycle of the clock, because you can't apply this equation to each and every logic stage in the design. You must, basically between the primary inputs and the primary outputs of the design, the sum of the excess delays over the clock period must be less than t clock high min. Since the number of pipeline stages between the primary inputs and the primary outputs can be tens of thousands, this means that only a few stages can use this particular technique to go faster. Or you share t clock to high, the high period of the clock between all those thousands of stages, which of course would be a minuscule enhancement. This point is illustrated in this example here. Here I have 3 stages of pipeline with 4 latches, and you'll notice that T1 and T2 are both greater than t clock. We're using cycle stealing because there's critical paths within that. The question is then, what is the constraint on T3 now? In this particular example, when the arrival time of D at this point here is now exactly at the falling edge of the clock going to that latch. Well, the answer is that T3 is now constrained to be t clock. That is, we've used up all the potential for cycle stealing in this chain of logic, this chain of synchronous logic, and now because it's all used up, we no longer have the flexibility of cycle stealing in order to make logic faster. So that illustrates why while this can actually lead to an increase in clock frequency, it's not as dramatic as you first might think. Let's look at hold violations. The difference between the equation here and the equation for flip-flops is, again, this t clock high. In this case, the maximum t clock high. If the logic is so fast as to change during t clock high, you're actually getting race through because of the transparency of the latch. An example with the hold violation is illustrated here. Again, the worst case scenario is when the right hand clock is retarded with respect to the left hand clock. The point is that we don't want D2 to change between this time here and this time here, which now includes t clock high max. In this example, that is happening. We have t clock to q here, t logic here. That is leading to a race through problem where D2 is changing during the high transparency period and certainly before the end of the hold time. That is leading to Q2 changing around the same clock edge. Notice that Q1 and Q2 are both changing with respect to the same clock edge. This of course is race through, which leads to incorrect logic operation. Now, because the variation between the logic under the fastest conditions for the shortest chain and the logic under the slowest conditions for the longest chain is so large, it actually becomes very hard in practice for latch-based designs to meet setup violations and hold violations simultaneously. And you can see in this example here, the shortest chain under the fastest conditions would actually have to be pretty long in order to prevent hold violations. This is why we don't use latches in design, because it can be very hard. It can require the insertion of a lot of logic, or it might even be impossible to satisfy setup and hold simultaneously. So that brings us to the end of this submodule. I remind you that latches are transparent while T-clock is high. This leads to an opportunity. You can actually potentially slightly reduce the clock period by enabling cycle stealing, which allows you to share this T-clock high along a chain of synchronous logic. However, it greatly increases the susceptibility to hold violations and greatly complicates the repair of hold violations by inserting additional delay. So thank you very much, and please now do the submodule quiz before moving on to the next submodule.